Welcome to this session. My name is Ajit Subhash Suryanshi from Department of Electronics and Telecommunication Engineering from Walchand Institute of Technology, Solapur. Today's topic of the discussion is logic gates and Boolean algebra. So at the end of this session, student will able to recall the logic gates and solve Boolean expression. Content of this session is first logic gates. In logic gate, AND gate, OR gate, NOT gate, Nand and Nor gate, Xor and Xnor gate. Also the realization of the basic gates using universal gates, and what are the basic gates and universal gate we will see later. Boolean algebra. First, NOT gate. It is also called as an inverter because it has a single input, single output. So input is A, output is read as A complement or A bar. And truth table of the NOT gate is where A is input, Y is output. So symbolic representation for the 0 is low and symbolic representation of 1 is high. So when input is low, output is high. When input is 1, output is low. So that's why it is called as a inverter. So same thing, what happens when two inverters connected one after another? You can see A is A, input becomes A complement, and after again giving as a input to the second NOT gate, what happens? It double complements becomes again A. So which can be verified with the truth table that same output is the same as of the input. AND gate. So AND gate is two input and single output AND gate. So AND gate may be a multi-input also and single output. So in the multi-inputs there are 3 inputs, 4 inputs, 5 inputs, 6 inputs, 7 inputs, multi-inputs. But common minimum input for AND gate is 2 input AND gate. Here inputs are A and B and output is Y. So truth table of the AND gate is A, B, Y. A, B are the inputs and Y is the output. So when both the inputs are 0, 0, that is low, low, output is low. When one of the input is 0 and other input is 1, it is a 0, output is 0. When one input is 1, other input is 0, output is 0. Only when when both the inputs are 1, 1, that is A and B is equal to 1, output is 1. So it is read as a Y is equal to A and B. So A dot B also. OR gate. So OR gate, it is a 2 input, single output. So in the 2 inputs, A and B are the input, Y is the output. When both the inputs are 0, 0, low, low, output is low. When one input is low, other input is high, output is high. When one input is 1 and other input is 0, output is 1. So when both the inputs are 1, that is high, output is high. So only case the output of the OR gate is 0 when both the inputs are 0. Otherwise, OR gate output is 1. So it is read as Y is equal to A or B. It is read as Y is equal to A or B. NAND gate. So NAND gate can be flipped as a AND gate connecting OR gate after that, or connecting NOT gate after that, sorry. So in the NAND gate, Y is equal to, it is read as Y is equal to AB whole bar, AB whole bar, or A and B complement. So it is again 2 input, single output. So in the 2 inputs, AB, when both the inputs are 0, output is 1. when both the inputs are 1, output is 0. The only case when output is 0 is when both the inputs are 1. Otherwise, output of the NAND gate is 1. NOR gate. When in a NOR gate, so NOR gate is, which is read as where y is equal to a or b complement. So it is or a or b bar. When both the inputs are 0, truth table for NOR gate, when both the inputs are 0, that is low, output is high. When one input is 0 and 1, output is 0. So all other cases output is 0. The only case when output is high is when both the inputs are 0. XOR gate. So XOR gate is exclusive OR gate. So XOR gate is also called as inequality detector. And why it is called as inequality detector? Same here, for XOR gate, inputs are 2, output is 1. So in the XOR gate, the logical expression for the XOR gate can be read as y is equal to a XOR p. So when both the inputs are 0, output is 0. When, in short, the truth table can be concluded or summarized as when both the inputs are same, output is 0 for XOR gate. Otherwise, output is 1. So that's why it is called as an inequality detector. So inequality detector means output is high when both the inputs are different. So reverse for the XNOR gate. So in the as a XOR gate is called as a inequality detector, and XNOR gate is called as a equality detector. When both the inputs are same for XNOR gate, output is high. So XNOR gate can be waived as connecting XOR gate and after that connecting the NOT gate. So the logical expression can be read as y is equal to a XNOR p. Then universal gates and its realizations. So which are the universal gates? NAND gates, NOR gates. And why these are called as a universal gates? Because so implementation of the all other basic gates are possible with the NAND or NOR gate. So this is a NOT gate implementation using a NAND gate. So when both the inputs are make a common and make a single input, it become a NOT gate. So NOT gate using a NAND gate. So this is a realization of the NOT gate using NAND gate. So this is a realization of the NOT gate using a NOR gate, making a input common. So realization of the AND gate using an AND gate is you need a 2 gates. So in these 2 gates, you can realize the AND gate with the help of the 2 NAND gates. AND gate realization NOR gate requires 3 NOR gates, and OR gate realization using NAND gate requires 3 NAND gates. So in this way, you can have or you can realize the basic gates using this universal gates. Universal gates are NAND and NOR gates. So Boolean algebra. What is meant by the Boolean algebra? Boolean algebra is the logical expression for all these logics we have studied. So the logic we have studied is AND logic, OR logic, NOT logic, XOR logic, XNOR logic. So duality applies to so in Boolean algebra, 2 main theorems are there. First is the duality theorem and other is the De Morgan's theorem. In duality, all Boolean expressions follows the duality theorems. So in the duality, a plus is replaced with the dot, that is OR is replaced with the dot, zeros are replaced with 1 and 1 is replaced with the zeros, and variable remains as it is. And in the De Morgan's theorem is the complementing the Boolean function and replacing the OR operation with the OR operation with the and 0 with the 1 and 1 with the 0. So this is the De Morgan's theorem. And these are the some Boolean theorems in a plus b, a plus 0 is equal to a, and its dual is 0 is replaced by 1, it is become a, and so this is a plus 1 is equal to 1, and the 0 is replaced with the 1, and this AND operation is replaced with the OR operation is replaced with the AND operation. Okay, so when a plus a also becomes a dot a is equal to a. So these are the common identities in the Boolean algebra. So let us come to the practice of some problems. Here, solving a Boolean equation means it is representing the Boolean equation in a convenient form or in the reduced form. So hardware required for realization requires minimum. So here a dot a plus a b dot c can be simplified to the a, and here a complement a or a dot b dot c can be replaced with the a complement b c, and these two problems are for the practice. So you can practice these problems and let me know the result of these problems after solving by using Boolean algebraic theorems. So these are the acknowledgements. Thank you.